Morning. Thank you all for joining us this morning. We are going to get started with today's presentation, which is Xenotransplantation. My name is Kelly Dowling, and I am the Executive Director here at the Kidney Foundation of Ohio. And I have the pleasure of getting us started this morning with a terrific presentation that will be given today by Zoe Stewart Lewis at the University Hospital's Transplant Institute. We're very fortunate to have today's session sponsored by Eaton. So thank you all for being part of today. Just a little bit information if you're not familiar with the Kidney Foundation of Ohio and our services and programs. We've been in existence since 1950, and we serve a 32-county service area in Ohio, and we also support 5 counties in West Virginia as well. We have 2 chapter affiliates in Lake and Summit County, and our main programs and services really include a broad-based program of direct assistance for those that are facing kidney disease. We also provide educational programs for the general public, renal professionals, patients, and their families. We really remain the only health and human service agency in the state of Ohio that provides direct assistance back to patients that are going through the devastations of kidney disease. And what's really important about us is that we're Ohio-based foundation, and that all of the funds that we raise here in Ohio stay here in Ohio to help our patients. Again, I want to thank Eaton for being today's and the remainder of the years and this past year's sponsor of our webinar series. Just a couple housekeeping items. Today's session will last a total of 1 hour. If you have any questions, please do submit those using the Q&A feature that's on your screen, either during or directly following today's presentation. And if time permits, those questions will be answered at the conclusion of the session. And Dr. Lewis has also mentioned that she'd be happy to answer those questions and follow up with anything after today's session if any remain. This session will be recorded and will be sent out to today's participants. However, if you are not watching this live, CEUs are not going to be available. For future sessions, visit kfohio.org, and we have a great starting lineup for 2024 series. So if you are not already on our e-newsletter, please reach out to us. You could sign up on our website as well, and you'll be added to the list for future webinars and other activities we have going on. Just for our CEU information, sepses are available today as a designated approved provider by the American Board of Transplant Certification, ABTC. University Hospitals Cleveland Medical Center will grant up to 1 Category 1 continuing education points for transplant certification for this particular offering. If you fill out the evaluation, then you're able to receive the sepses after today's session, and those will be emailed to you within 48 hours. I have the pleasure of announcing our speaker for today, Zoe Stewart Lewis, who is at University Hospitals. She's the Chief of Transplant. She's also the James A. Shulak Endowed Director of Transplant Institute and University Hospitals of Cleveland. Zoe has been with and in the Cleveland area since April, and we're very lucky that she's part of our community and to share the knowledge and resources that she has and what she's experienced through transplantation. And Zoe, I'll kick it over to you. We look forward to your presentation today.
Great, thanks. I'm going to start to share my screen. Okay, great. Try that one more time. The right one. All right. And you guys are seeing the slides?
Yes, we can see them.
All right, beautiful. All right, so I do not have any disclosures that are going to be relevant to this presentation today. Oh, and I actually should start out by thanking Annette and Kelly and the rest and the entire KFO for this opportunity. I'm very pleased to be participating. So just to kind of give us and lay the groundwork for this talk, I think it helps to really kind of have a good understanding about the scope of the problem and the scale of what we're talking about. So this is a slide from the United Network for Organ Sharing, and it's summarizing the 2022 year in transplantation here in the US, which was another record-breaking year. Again, the total number of transplants performed in the United States increased, and it was nearly 43,000. For the first time, we performed over 25,000 kidney transplants. Just to give you a sense of the rate of growth, and I'll show some of that in a second on other slides. When I was a transplant fellow, we're not going to talk about how long ago that was, but we were doing about 16,000 kidney transplants a year. So, a very real significant increase in the number of kidney transplants year by year. And the other organ groups also set records. So liver, heart, and lung transplants also had all-time record highs in 2022. So despite sometimes some of the negative press about the US transplant system, we are doing some great things, clearly. So this is, again, a data that is showing about the gap between the waiting list and then the number of transplants being done. And again, the number of donors in the blue line here on the bottom. So again, year by year, you can see that the number of donors does continue to slowly increase. Apologize if you're hearing the helipad outside my office. They're landing, I think, right now. And then the number of transplants, again, more notable uptick in the more recent years. And these are all very promising and great things, but the unfortunate reality is the burden of end-stage organ disease in the US really far outstrips the current pace of available donors. And so again, you can see that the waiting list well over 100,000. When we talk about the waiting list and the organ shortage crisis, I think, again, there's no question that one of the largest gap clearly is within kidney transplantation. And it just has to do with the reality of end-stage renal disease being so much more prevalent. Common risk factors, diabetes, obesity, hypertension, all of these kind of tie into a lot of, and lack of access to good primary health care, to a lot of core problems within our US population. And so again, we see a very high burden of kidney disease. The kidney waiting list in terms of active patients is over 90,000. And again, despite us doing 25,000 transplants, we're clearly continue to have a very large gap on the kidney side. And again, other organ groups still have a bit of a gap, but certainly nothing on the scale of where the kidney is. And again, this is the data from 2021, and it's certainly not terribly different today. Unfortunately, nearly 20 people die each day waiting for an organ transplant here in the United States. So we talk about kidney transplantations. There's different ways we can think about this population and how they may leave our organ transplant waiting list. So again, it's great to see that if we look at the total number of patients that are leaving the wait list, that this blue circle, about 20,000, and this is, again, data I should mention from 2017, but again, this distribution continues to look similar year by year. And, it's great to see that nearly 20,000 people got transplanted in that year. Unfortunately, there were another 4,500 patients that became too sick for transplant, another 4,400 who died on the waiting list. So that's 9,000 patients. So about a third of the patients are leaving the kidney transplant waiting list clearly in the wrong way. So there's been a lot of focus and continues to be a lot of ongoing focus on ways to increase transplantation. And in particular, a lot of the conversation does center around deceased donor transplantation, and that will be the bulk of what I'll talk about today. But there's been a strong push in the United States to increase the use of donors after cardiac death. This is great in that we're pursuing more organ opportunities, but the reality is a lot of these donors are older DCD donors, and many of these kidneys are not going to ultimately be suitable for transplantation. So we talk a lot about the fact that we have increasing non-utilization of kidneys that have deceased donor kidneys that have been recovered with the intent of transplant here in the US. And while on one hand, I think we never want to not be utilizing organs that are appropriate for transplant, I also do think that there is a component of this that is clearly reflective of aggressive work by the organ procurement organizations at pursuing every donor opportunity so we don't miss the potential for a transplantable organ. So I personally don't think it's a terrible thing that we have increasing non-utilization, because I think this is mostly reflective of the fact that we're being really aggressive at pursuing every potential donor. And that is the price or the reality of pursuing every potential donor, is there will be non-utilization of some of those donor organs. Certainly, it's important that we continue to stress public education about organ donation and the importance of being an organ donor. Despite a lot of these efforts, though, overall organ donation rates, as I showed you on one of those early slides, remain relatively flat, both for living donation and deceased donation. Just to touch for a tiny bit on living donation, the unfortunate reality in the United States is there continue to be real disincentives for potential living donors. And what do I mean by that? Another way of phrasing it perhaps would be there's real barriers for many people who might be interested in being a living kidney donor. And these barriers to being a living donor can include mainly the fiscal aspects of it. And so this could be lost wages. You can't work for a period of time. There can be the cost to travel if you're, not doing your donor surgery locally, and not all travel costs would be reimbursed for potential donors. There's the costs for maybe childcare. All of these things are barriers for many people who might otherwise pursue living donation. So if we could in the US in the future move to a system that actually can truly make living kidney donation fiscally neutral for potential donors, I think that may be one way to sort of attack the living donor piece. Again, there's been a lot of great work done in the domain of kidney paired exchange, so that again, the reality is 1 out of 3 potential living donors and the recipient will be non-compatible for living donation. Again, I'm dating myself here. When I was a surgical resident, if a donor came forward and was fit and healthy and cleared all of the screening tests and was willing to move forward, but they were blood type incompatible, they were told, sorry, you're blood type incompatible. And they were just told, you can't be the donor. And the recipient was told, you need to go find another, potential donor. And so again, that's 1 out of 3 potential live donor recipient pairings. So kidney paired exchange has really certainly helped address and overcome that barrier, at least. And so that when we do have fit and healthy and willing potential living donors, we can at least have paired exchange to allow those opportunities to make, an impact. Again, the reality, though, is in the scale of numbers, this is an incremental impact on the scale of the problem. Certainly, we continue to have a lot of research in the area of technology to expand the utilization of so-called marginal organs. So again, that every potentially transplantable organ can be used. Certainly, this has had in the last few years the most notable impact with normothermic perfusion devices that has significantly increased our ability and utilization of DCD livers and hearts without impacting, patient outcomes. This is again just data provided by UNOS you can see on the x-axis by transplant year. And again, it's just an overall breakdown on the number of deceased donors. So as I mentioned earlier, you can see we've really been pushing, pursuing every potential deceased donor with an increased emphasis. And again, the bulk of this has been in the area of donors after cardiac death, this lower kind of orange bar. You can see we've gone from, being, 10% of potential donors up to now about a third of the total donor pool are going to be DCD donors. And again, a smaller incremental increase in the brain dead donors. So again, a third of our donors are now DCD donors. And so not just DCD donors, but older DCD donors many times. And so again, a lot of these organs may not ultimately be truly transplantable. So what if I told you that there may be a way that we could fix and address all of these problems now? How would that be? That way could be xenotransplantation. So it's what we're here to talk about today. So kind of the backdrop to this, some of the very first work in this, or first kind of foray into some of these domains, really actually occurred back in the 1600s when xenotransfusion was actually being performed. So they would use the blood of lambs and transfuse humans with this. There were not, surprisingly to me at least, there were not immediate deaths from this, but the patients usually would succumb for other reasons. And then as we got into the era of modern human blood typing, which was right around the turn of the century at 1900, this practice really became abandoned, and we would do human-to-human blood transfusions. So as we talk about xenotransplantation, the concept of using organs from animals and transplanting them into humans, there's just some sort of basic starting points to that conversation and that concept. So certainly one very basic question is, which animal would be appropriate for this? First kind of thought might be, well, non-human primates, so baboons or other, again, primates, would be the most genealogically related to humans and the most similar from sort of an anatomic standpoint, with the organs, size matching perhaps, and also just sort of, similarities to some of the other signaling pathways, antibody productions, etc. The challenge with this is, non-human primate model is really not scalable, right? So, and what I mean by that, it just the realities of the gestation period and the litter size for non-human primates isn't going to make it a practical and realistic solution for xenotransplant. So, this certainly shifted focus and interest into pigs. So pigs offer many advantages. They actually have similar anatomy to the key organs that we're talking about, and similar, physiology, certainly within like the kidney function. But they are a bit more evolutionary divergent, certainly, than non-human primates. And then, of course, when we talk about other barriers, the immunologic barriers. So again, when we're talking about doing allotransplantation or human-to-human transplantation, we already have immunologic challenges there, versus now talking about adding in the differences between species. And certainly, baseline, this does create the need for much higher immunosuppression for recipients. And that's, again, unless we do some sort of gene editing to the animals. And then the other kind of, I think probably, more recently recognized concerns are zoonosis. So again, animal-derived infections that could come and be passed along from, the animal organ into the recipient who's on immunosuppression and more vulnerable to these infections. And how do we protect the patient? How do we protect family members? How do we protect medical staff from the potential risk of a zoonosis occurring? So certainly early on, when we even started the, allotransplantation, human to human, the first barriers that had to be overcome with immunosuppression was hyperacute rejection. And that was certainly the first barrier that was recognized with using pig donor kidneys for human transplantation. And so, work identified early on that the hyperacute rejection that occurs between a pig donor kidney and a human recipient is mediated by natural antibodies that humans have to pig antigens present on their cells. And this would lead to, rapid activation of complement cascade, and this causes rapid clotting in the kidney and immediate failure of it. And so what was first recognized as one of the first major steps forward was recognizing that the major target of our human antibodies to pig kidneys is actually a carbohydrate epitope, which we call alpha-gal That's why I'm going to refer to it for the rest of this talk, alpha gal, or just, gal. And this again has this carbohydrate, this sugar epitope, is very highly expressed on the endothelial cells of pig donor organs. And so again, if we were to transplant organs from pigs that contains this carbohydrate epitope, no amount of immunosuppression is going to overcome the antibody attacking and causing that immediate graft failure. And so this led to the development of alpha-gal knockout pigs. So pigs that have been genetically modified to have that gene knocked out, and then again, they are born. And so again, we can have pigs that are lacking both gene copies of this and are truly knockout pigs. And fortunately, it's sometimes when we make a gene knockout in animal models, such as mouse models or pig models, when we knock it out in that animal, it's a fatal knockout because there can be other required functions of that for the animal to be healthy. But alpha-gal can be knocked out, and the pigs are actually quite healthy and have normal gestation and development, etc. So it's not a knockout that causes a deleterious impact in the pigs from that standpoint. There are actually alpha-gal knockout pigs, as an aside, were actually really more developed because there are some humans who have a high intolerance to any pig product, whether it's eating pork or bacon or other products, or some of the medications such as heparin, for example, that are made in pigs. And so again, these are actually FDA approved alpha-gal knockout pigs because again, they can be used for that purpose. So I'm gonna, in the next couple slides, really do a 30,000-foot overview, quick summary of over 2 decades of extensive research with pig xenokidneys. So again, pig kidneys being transplanted into non-human primates, typically a baboon model. And so again, all of these research efforts really, were critical and led to critical understandings that underpin where we are currently at in the field of xenotransplantation. At the outset, though, I think it's been recognized, unfortunately, that despite a lot of the important lessons we did learn with these studies, at the end of the day, even though it's a primate model, there really is not direct correlation to human HLA, our human protein reactivities, and our human response to the same pig xenograft. So what do I mean by that? If we take a pig kidney and we're to put one into a human and one into a baboon, the immune responses are still going to be very different, and the immunosuppression needed isn't really going to be the same. So the hope had been that there would be enough similarity that we could develop really very directly translatable immunosuppression protocols and monitoring, etc., in the baboon model that we could then just carry right over into human clinical trials. And unfortunately, that's not the case. The HLA differences between baboons and humans are enough that it is not directly translatable. Certainly lessons that were learned, though, is that overall, and again, this was pretty intuitive, I think, to those of us in the field, the immunosuppression protocols for xenotransplantation, even with gene-modified, genetically modified pigs to try and make it more favorable, even in the current state of things, the immunosuppression that's going to be needed to support a pig xenotransplant kidney is going to be much more intensive than the immunosuppression we currently need to do a human-to-human kidney transplant. I think probably some of the most important work from the baboon, the non-human primate models has been, a lot of other important signaling pathways beyond just the alpha-gal carbohydrate epitopes have been sort of recognized to be important when we think about xenotransplant. There are other important compatibilities that have been identified between pig and human proteins. And again, I just highlighted a couple here and here, and just, in a nutshell, some of the clotting factors that between pigs and humans, have, reactivity, and aren't, directly translatable. And so again, all of these things become important when we start talking about a solid organ transplant, because again, these are going to increase the risk for blood clots forming within the transplant organ, which can of course cause the allograft to either fail or have poor or shortened longevity for the recipient. When we talk about, I don't want to get too in the weeds on this, but when we do talk about the genetic modification of pigs for xenotransplantation, there's two different ways that we do genetic modification. One is what I described for you previously with the alpha-gal, which is to completely knock the gene out of an animal. And so that's just, we call that a knockout. It's exactly like it sounds. The animal will have absolutely no expression of that gene, doesn't make any of the, either carbohydrate or protein, produced by that. And so again, complete knockout. Again, there are many of the recognized important proteins in xenotransplant involve coagulation cascade, the clotting factors. We can't just knock those out in pigs because it leads to fatal. It's fatal either embryonically or shortly after birth. And so we may need to do transgene expression, where we try to have tissue specific expression of things through kind of complex genetic modifications. I'll kind of keep it at that. The challenge with doing transgene expression, trying to sort of turn on or turn it on a little bit, a gene expression, is that as you do subsequent breeding of animals, the transgene expression will vary among subsequent generations. So it's not like it's stable over time. And obviously, when we talk about xenotransplant, we need to have a genetic model where it's going to be very stable and very reproducible and we know exactly what we're kind of putting into a recipient. The other challenge is even within a transplant organ, when you transplant that organ, we currently expect, our transplant organs, certainly kidneys, to have a longevity of, at least 10 years for a deceased donor kidney, and obviously living donor kidney, we hope for 20 years or longer. Well, with transgenes, over time in an individual, the transgene expression will change, and so and can sort of fade. And so again, you can imagine if we put in a genetically modified pig kidney that has modified transgene expression, and then if 5 years later there's different expression of that transgene, that again can we don't know what that really means for the recipient long term, and it may be difficult to have that be reproducible and predictable for every recipient. And so again, that can pose significant challenges for having a consistent xenograft for transplantation. And so that challenge with transgene expression really was the underpinning for the genetic model we used when I was at NYU, which was to really just use the alpha-gal knockout pig for the first human decedent experiments. And I'll talk a bit more about that. So when we start to think about doing, clinical trials and, trying to take that decades of work that I told you that had happened in non-human primates with pig kidneys, and to think about moving this into human clinical trials, there was a lot of, thought put into how can we bridge this very large gap. The schematic I have up here isn't showing you a terribly large gap per se, but there's this gap from one side to the other. You're standing on this side and where we were with the non-human primate model, and we're trying to get over here by the flag into doing, true human, trials with this, and how could we perhaps bridge this? And so the intermediate step that was first taken was to do pig xenotransplantation into whole body deceased organ donors. And I'll talk more about this, what I'm going to call decedent xenotransplants. So decedent human transplant models. So these are donors who are brain dead. So they've been declared legally dead, just as others going forward with organ donation would be. but they have a hard stop contraindication to standard organ donation. So this could be something like a malignancy. They could have either a current or a recent, solid organ malignancy that makes them unable to be a organ donor, or they could have active infections. Sometimes there are certain infections in a donor that we can't just treat through and still move forward with trying to transplant those organs. So again, brain dead donors. And in this situation, when we started out with this model, and again, it took, years, 5+ years of work with ethicists, with patient focus groups, stakeholders, with organ procurement organizations, you name it, to really get to this point of creating the model and system for how we would approach family members for consent for whole body donation for the purposes of these clinical trials. So initially, the initial ones have been limited to patients who had been self-registered as an organ donor. So again, if an individual's brain dead, they were registered on one of the donor registries, and they had a contraindication to being, a donor, then the family would be approached for consent for whole body donation for xenotransplantation. In this situation, was a very extensive consenting process. And it's a very different situation, as you can imagine. In this situation, the donor is actually moved to the, where the experiment, the clinical trial is going to be taking place. So in this case, we would transfer the patient to NYU, and then they would be monitored there the entire duration of the post-transplant period of time. This also included, we had to work through protocols on, we couldn't just, bring this donor into our standard ICU and then put a pig kidney into them and have the patient with a pig kidney in a standard ICU. We couldn't do it in a regular OR, for example, because again, the concern of zoonosis, we wouldn't want, surgical instruments being used for a pig xenotransplant and then sterilized and put back into standard circulation. You wouldn't want any of that equipment. You wouldn't want, nurses, going back and forth between the patients. We had to do extensive monitoring of, anyone involved in patient care was monitored and had to, do serial blood draws to monitor for zoonosis. And so a whole kind of standalone ICU had to, for the purposes of clinical research, had to be created with and staffed with, anesthesia intensivists to care for them. Because again, these patients are an ICU patient. They're intubated, they're on, pressors, et cetera. And they need, very close monitoring to be maintained as stable. And then we had to have an OR suite that we could do this in as well. For the NYU model, our model was to keep it as simple and clean as possible. Was we did not do native nephrectomies. So the donor's native kidneys were left in situ, and one pig xeno kidney was transplanted externally onto the femoral vessels. And then we could directly cannulate the ureter, and we could, continuously visualize the kidney, and we could continuously capture the urine produced directly by that pig kidney. The other center that was kind of currently doing this about the same time was at University of Alabama, and the UAB model was to do a laparotomy on the whole body donor, remove the native kidneys, and then to put 2 pig xeno kidneys transplanted intra-abdominal. And again, the rationale with that model was any kidney function that was seen or any change in serum creatinine could all be attributed only to their 2 pig xeno kidneys. And again, both models clearly have validity and benefits to them. Certainly we don't routinely transplant 2 kidneys, in human to human transplantation. So that was also one of the reasons why we wanted to do one xeno kidney in the NYU model. So again, this is just a schematic of the NYU model. So again, we have our, gene edited, the knockout gal pig. We recover the kidney. The one other modification, I don't want to get too far in the weeds here, was The pig donor kidneys also had a little bit of pig thymus under the capsule. And again, the thymus produces some, white blood cells, and this was thought to, again, and these thymo kidneys, or as they're called, had been studied previously in non-human primate models, and were thought to help reduce the immune response because of the production of the cells from the thymus, the pig thymus. But so there was this modification as well. So this kidney was then again implanted on the thigh. So we have our patient being monitored, and then we had the external modeling here. So this is what it looked like in reality. So this is our paper we published in the New England Journal of Medicine about the first 2 cases of pig to human kidney xenotransplantation. And again, so this is an incision made over the femoral vessels in the groin crease. And again, we can do our vascular connections and then just directly cannulate the ureter. There's some notable differences. So we tried to utilize kidneys that would be similar in size to standard human kidney. So these were juvenile pigs, about 400 pounds. A couple differences: they had a very thin capsule on the kidney, which again, you probably don't appreciate this picture with somebody who's a lot of kidney transplants. This is a very kind of abnormally thin capsule, and they have a very large ureter, much larger, fatter ureters than we would see with a human kidney. But these were the first 2 kidneys. They reperfused beautifully. I will tell you, it was probably, aside from the birth of my kids, probably one of the most amazing moments of my life when the first kidney we did, and we had no idea what was going to happen. We didn't know if we took the clamp off, if the thing was going to turn black and not work. Instead, it pinked up just like we were putting in a live donor kidney and made urine, and it was absolutely amazing to see. And so we followed, this is the first one, or recipient number 2, about after reperfusion. And then again, we followed for over 48 hours, so over 2 days in these initial trials. And what we saw was immediate function. We saw, liters of urine being produced. We saw the patient's serum creatinine decrease, and I'll show you some of that. So this is how we kind of stabilize it over time. So we I concocted this where we could cannulate the ureter and then collect the urine directly. And then we just sewed on, this is a pediatric silo bag that we use for babies that are born with either gastroschisis or their organs external to their body. And so they don't have the abdominal domain for their organs to go inside, and we have to slowly, let them grow. And so we maintain and protect their organs with this bag that's sewn. So we took a pediatric silo bag and that's how we kept the kidney kind of moist and not getting desiccated when we followed it for several days. It also allowed us, we could just open this up sterilely and get a biopsy of the kidney, because we wanted to be doing timed biopsies so we could look for any signs of rejection and other changes within it. So this is a picture of us actually at the time of this kind of went around to a lot of places. So this is myself, this is Dr. Montgomery, this is one of my other partners, Dr. Bonnie Lonzi, and this was our fellow, Dr. Jeffrey Stern. He and I had gone and procured the kidneys down at the facility at Revivicor down in Virginia, and then we flew back with them and transplanted it. So that was the first step at the NYU model. This past summer, obviously the next step was to see if we could extend this beyond 2 days. Could we actually do, more durable, longer term function? And you have to think about what this means for this donor family. I mean, it's an incredible gift that they are giving to help, future patients. So this is the donor from the study over the summer. This is Mo Miller, and he collapsed suddenly and unexpectedly one day. And when he went to the hospital, he was found to have a very large head bleed, secondary to a completely unknown large glioblastoma. And he had previously indicated he wanted to be a donor. And obviously, unfortunately, with a GBM, he could not be an organ donor. And so his sister was approached as his next of kin, and she felt very strongly that this is something he would have wanted to do. But you have to imagine, you're asking the family to pause on their ability to, have a funeral and have the closure, after end of life, and in an unexpected situation too, not like they had any time, to prepare for this. So again, they used the same alpha-gal knockout with the pig thymus. In this situation, for this, because it was going to be a longer study, it wasn't, going to be feasible to think we could keep the kidney connected, for 2 months in the sort of initial proof of concept location on the femoral vessels. So the native kidneys were removed, and a single pig kidney was transplanted intra-abdominal. And again, this continued through 60 days, and there was no sign of rejection and maintained normal function. And this was, again, with fairly standard immunosuppression. I'm not going to get into the weeds too much, but again, not something that would not be feasible or realistic to use in an actual clinical trial with patients. And I'm just going to briefly talk about the UAB experience. So this was led by Dr. Jamie Locke. Actually, Jamie and I were, strangely enough, we started surgical internship together at Johns Hopkins, and we both ultimately matriculated into transplant. And she's down at UAB doing similar things as I ended up doing at NYU. But her team, as I mentioned, did bilateral nephrectomies and then implanted 2 pig kidneys. The one major difference was the donor pig in their model. So they are using a pig that has had 10 genes edited. So there's 10 different genes that have been modified within this pig. Some are knocked out, most are transgene expression. And then again, they monitored it through 74 hours. Despite transplanting both kidneys in this model, the serum creatinine did not decrease in this first trial, and despite urine production, they weren't seeing a lot of excretion of creatinine into the urine that they had collected in this initial trial. They then similarly over the past summer months did a longer trial where they did carried it out for over a week. And in this situation, they found that they had immediate graft function in this situation. So again, they put in 2 kidneys. You can see this green line, blackish looking green line, the decrease and maintenance of normal serum creatinine. And again, when they measured formal creatinine clearance, again, all very robust. The one difference that they did with their protocol was this time they added in an immunosuppression agent called eculizumab to their protocol. And this is something that really targets and shuts down activation of complement-mediated antibody rejection. So how close are we? Before I jump into some of this, I'm going to briefly talk, and the focus of this is obviously on kidneys today, but many of you on the call may have seen, the well-publicized reports of the 2 cases where the University of Maryland has performed pig xenotransplantation of a pig heart into a human. And so the first one was done as a FDA authorization, and that individual survived for 8 weeks after this transplant of the pig heart. And he ultimately succumbed to kind of multi-organ failure and graft failure and sepsis, but also was part of the issue was thought to have been porcine CMV or cytomegalovirus. So we certainly within allotransplantation, human to human, have to deal with CMV infections from immunosuppression, either reactivation or somebody's not been previously exposed. We can have de novo CMV, which can at times be, human CMV can even be fatal at times in, transplant recipients. And so there was some concern that the porcine CMV may have contributed to that allograft outcome. And then the second heart transplant happened at the end of summer into September. And that patient, and the difference they made was they modified their protocol for following the pigs on the donor pigs on the pre-side to ensure that they screened and were certain that the pigs did not carry porcine CMV. That individual ultimately lived 6 weeks, and it wasn't entirely clear why that heart failed at 6 weeks. Again, it wasn't an obvious antibody-mediated rejection process, although they're still yet to sort of fully publish their analysis of that. And so again, part of the reason why the FDA authorized, I think, the heart, trials directly into a recipient, an actual recipient, is, these were individuals who were going to imminently die from their heart failure. And, it's not the same situation as patients with kidney failure who do have dialysis. While not ideal and certainly not as good as we know as a functional transplant, we do have a very reasonable alternative therapy with end-stage kidney disease, whereas with heart failure, once you've exhausted mechanical support devices, there is no alternative. And then NYU has also, and this also was when I was still at NYU, done several, I think at least 3 or 4 pig hearts into whole body deceased organ donors. And again, followed them out for several days with excellent heart function, et cetera. But again, we still clearly need to have a better understanding of why the hearts are failing, at 6 to 8 weeks. The other challenge with hearts, probably more so than kidneys, is that the pig heart can grow, because again, we're using juvenile hearts, and there's concern about in the non-human primate models, that was an issue. And so part of the 10 gene edited model does include trying to have a modification of growth hormone to try and limit the growth of the organ once it's implanted. So I just wanted to also just briefly mention this other and very, very important work that's been going on in xenotransplants. So how close are we? We still have a long way to go. We've made some tremendous steps, but we really still don't know what the right immunosuppression protocol is. I think the immunosuppression protocol is going to be, different depending on which genetic xenograft you're using, whether it's the alpha-gal knockout with thymus versus a 10 gene edited pig. As I mentioned, we certainly don't have an understanding of which of these genetic models with regards to kidney specifically is going to allow the best longevity. As I said, there is a lot of concern that the 10 gene edited transgene model, we won't have stable expression of genes, for 10, 20 years, which is what we obviously are looking for on the kidney side. I mean, for any side, but certainly with specifically to kidney. So again, it's just not clear what the right genetic model is yet. That is yet to be sort of settled and determined. And then again, there's still ongoing concerns for zoonotic disease transmission risks. We don't know what we don't know with regards to that. That is my last kind of formal slide. So I'd be happy to take some questions.
Thank you so much for that presentation. It was incredible, so informative, and it's so nice to hear about what's going on around us that we are not all familiar with. So Zoe, thank you again for that. So please don't forget to put questions in the Q&A feature or in the chat of Zoom. Just a couple for you before the questions start rolling in. Zoe, what do you or could you see as the next possible animal down the road as a future option if pigs are no longer an option, or they can choose something else?
Yeah, I think pigs are going to be, it's going to be pigs. It's a short answer. I'm sorry, the helipad's going. I swear to God, it hardly ever goes off. It's only like the 1 hour I'm doing my talk. Hopefully you guys aren't getting too much background on that.
No, you're good.
Good. I think the reason that pigs are such an ideal model, aside from the fact that we have almost 30 years of research with the pig model. So to think that we would move to a different model is sort of hard to we'd be kind of starting all over again with the same challenges. But I think the reality is the gestation period of pigs and the size of their litters, right? So if we think about needing, 100,000 kidneys, it makes it attractive from that standpoint. So.
Okay. No, that makes total sense. Since you've been a part of this and you've literally seen this hands-on and really been there for the surgery, what is most exciting to you? What has been the most exciting portion of this that you could share with all of us, so that we can kind of feel that excitement there with you?
Yeah. I mean, I think it's just it's the excitement of thinking how many patients we might be able to help, and yet, I think we're going to see this in my, probably the tail end of my practicing career, but certainly in my lifetime, like like the thought that we won't have patients, that we could actually get to the point where like almost no patient ever goes on dialysis, like chronic dialysis, right? That's a pretty exciting thought to think, right? And I think we're only going to get better and smarter at how we can do the genetic editing to again keep making and improving on a model where the immunosuppression is similar to the risks that we would take with a human to human transplant. So I think another kind of backward kind of question to back kind of the sort of reverse engineering to your question is the I just lost my thought. I had a great thing, I lost it. Dang it. This is what happens when you're up all night doing an operation. The shoot. It's on the tip of my tongue. It'll come back to me. I'll circle back. I know it's going to come back to me in a second.
We actually got a question in, so we can go
Yes.
this route. One of the attendees said, "Great presentation. Thank you so much for sharing your knowledge." This person said, "I know you mentioned that immunosuppression used in these trials are already available, but are there any targets that have been identified where it may make a difference, but the therapeutic hasn't been developed?"
Yeah, it's a great question. I don't think we have that granular level yet, because again, and part of that is I think some of that was worked out in our non-human primate models, but it's unfortunately not as translatable as we had anticipated it to be. For as we move into humans, and that's why we had certainly hit the point where we do need to be doing the work in clinical trials. I got my thought back, by the way. And I will add, just to finish up the last question, there are some of the agents used in some of these whole body deceased donor experiments have been agents that are not yet commercially available in a couple of the situations. And so, but there are agents that are close to being, kind of more broadly available. But, has been a little, again, we just don't know how much immunosuppression we need yet. And that's, the challenge for sure. And I think so. The thing I was going to mention is I do think, something I'm asked a lot is, well, what's ultimately going to be the best? Do you think this will get, how far away are we from being at the point where we won't do human to human transplant anymore? Like it would just be pig kidneys almost, like, right? Because everyone would get a preemptive transplant with the pig kidney. I mean, I think that day is a ways off. I mean, to think that we're, where we have to go from where we are now with the immunosuppression and the barriers there and what we need to do for xenotransplant versus if you have, a human organ available, it's going to be, we do really well with human to human transplant. The bar is really high, right? We have expectations of double-digit graft survivals. And certainly, with living donors, even longer. And so to think how long and before we're there with a pig kidney, I don't know, but I think, early on, I think the opportunities are going to be there to help, patients who are much older and on dialysis and are in that frame of they need to not be on dialysis because of what that's going to do to shorten their longevity. And because of their other health comorbidities, their lifespan is probably more realistically 5 to 8 years. I think that will be a group of patients that we may first be able to serve best with, pig xeno kidneys, and still kind of, I don't want to say reserve, but have, your younger ideal patients and recipients, that shouldn't be the first thing they do, because it's gonna, there's gonna be increased risk to that and consequences to that.
Yeah, that makes total sense. I have one last question for you. Actually, probably two. One for you is here in Northeast Ohio, I think we're very, very lucky to have incredible researchers and nephrologists and just physicians in general. Is there anything locally being done on this topic, or do you see it being something that's going to be coming up in the future here within our community?
Yeah, right now there's not of like the sort of scale like I've described to you. So, I mean, I haven't gotten into, I kind of alluded a little bit to the infrastructure that has to be in place to do this in terms of, dedicated animal husbandry facilities, that where you can raise them in a sterile environment. So again, you can, and zoonotic free environment. That's millions of dollars of investment for an institution to make there. And then you need the infrastructure from ICU, OR support, all of that. So this is not something that's like going to just, I think you're going to see it kind of at a few places still like UAB and in a way where they already, have been on the front end of having that infrastructure and partnering with, Revivicor, who really is, the owner of these pigs at the end of the day, and these genetically modified pigs that are the current, models we're working within. So, I mean, again, obviously, like anything, we will get to a point where it becomes more dispersed and more widespread, but, that's not happening like in the next 5 years. Like it's, going to take a bit longer than that.
Okay. All right. Well, we are out of time this morning. Thank you all for being a part of